we're going to start with the first plenary session of this conference, looking at climate change and population displacement. I'm very pleased to welcome our first speaker, Joanna Haigh, who is the co-director at the Grantham Institute. She was previously the head of the Department of Physics there, and she's published widely on the issue of climate change. Joanna, thank you. The floor is yours. May I move this up here?
Sure, of course.
Detach anything. And thank you very much for inviting me to give this talk. I should explain, I'm a climate scientist. I'm not an expert on populations or refugees, but I can provide a background on what might be happening around the world in response to climate change and how it might affect the way people live. So you will be very familiar with this plot. It's showing global average temperature from 3 different independent temperature records, and you can see that they largely agree. There's a spread of grey on there, which is a sort of uncertainty range. And sometimes you'll hear people say, oh, those scientists, they say they're uncertain, they don't know what they're talking about. But this is actually a range, sort of within that range is where we think it's going to be. This is a very complex system. It's not just a nice, neat experiment in a lab. And so the fact that the temperature's wobbling around...
Can you speak into the mic, please?
The fact that the temperature... I'm too loud now. The fact that the temperature's wandering around as well as going up is not at all surprising. So there's also been discussions about whether or not climate change has stopped. You've heard that particularly in the Daily Mail and things recently. It may have slowed down slightly, but it certainly hasn't stopped. It's carrying on going up. We've had the 3 warmest years on record recently. There's 2016 on the same plot. Other evidence, I'm not going to linger on this plot because I've got plenty of other things to say, but of course one of the most important ones is sea level change at the bottom right there, which is going up fairly intermittently in response to the warming planet, and of course which affects people around the coasts. But when we talk about global warming, we sometimes hear people say we want to keep global warming to within 1.5 degrees or 2 degrees or something like that. That's a global average. But it doesn't warm up everywhere by the same amount. So a 2-degree global warming doesn't mean to say that it's going to be 2 degrees here and 2 degrees in South America and 2 degrees in Africa. And this is a picture which is showing you how much the temperature has risen over 100 years or so across the globe. And the purple colours are where it's risen most, so about 1.5 degrees, and you can see that's largely over land masses. And the paler colours are where it's changed least. The little pluses indicate places where the statistics are fairly robust, so we can believe at least a sign of the change. And you can see it's varying hugely. In Africa, for example, it's going to be varying by getting on for 2 degrees over that 100 years already. In parts of the North Atlantic, there's no little pluses, so we don't really know what the sign is, but it's some indication that actually it's been cooling, which is a very interesting physics problem, but it doesn't mean that there's no warming going on. So sometimes you'll hear people, Boris Johnson's a good example, oh, it's cooler this year in Britain, global warming's gone away. That's just an oversimplistic and an incorrect interpretation. So that's looking at the data from the past. Of course, if we want to think about what's going to happen in the future, we not only need to do our physics and climate modelling and looking at that side of things, we also need to predict what the carbon dioxide content is going to be, and that's far more difficult because you've got to predict what the economy is going to do and what sort of energy sources people are going to use. So these are different scenarios from the Intergovernmental Panel on Climate Change, and you can see on the left there are various ideas on where energy might come from, and the one on the right is lots of coal, and the ones with more green are less. So that if you look in the middle panel there, that's the emissions of carbon dioxide according to those 4 scenarios. And the green one there is peaking fairly soon in terms of emissions, and then decaying down to 0 by the end of the century. The most extreme one there in blue is carrying on going pretty much as usual until the end of the century. But how the emissions respond is not the same as how the carbon dioxide concentration is, because carbon dioxide sits in the atmosphere at least 200 years before it's taken out by some process or other. So in the right-hand panel, you can see the response of the carbon dioxide concentration to the emissions in the middle panel. So even the green one, which has the peaking now and when it came to zero emissions by the end of the century, the concentration is still well above 400 parts per million, which is a key mark concentration by the end of the century. And we know for absolute sure that this carbon dioxide is coming from, so this is predictions, but the carbon dioxides we've had already are due to human activity and not due to any sort of natural effects, because we can carbon date the carbon molecules in the atmosphere, and they're old fossil fuels, so there's absolutely no doubt about that. In addition to which, the carbon dioxide is now higher in the atmosphere than it has been for probably 3 million years. Humans have only been on the planet for 200,000 years, so you can see life on Earth has never existed with the levels of carbon dioxide that we have now. Moving on, so that's the predicted response in global surface temperature to that, the most extreme and the least extreme. When you look at these plots, it's always a bit annoying because people have different reference levels. This level is relevant to about 2006 or so. So it's showing 1 degree above that by the time you get to the end of the century. This is already a good half of 0.7 a degree more than pre-industrial. So whenever you look at these temperature differences, make sure to check what it's difference to, whether it's pre-industrial, say 1850, or present, or sometimes you see the Met Office talk about, the middle of the 19th century. It's a bit of a pain, but just bear that in mind. And then the most extreme one there is going up by 4 degrees, or 4.7 degrees since pre-industrial, with a big range of uncertainty. And then, of course, we've got the effects varying across the globe. So the left-hand column there is the least serious emissions path, and the one on the right is the most serious. The top panel is temperature, and the bottom panel is precipitation. So if you look at the top right there, with the worst scenario, particularly you can see over the land masses, the temperatures are going up by 7 degrees, say. In the Arctic, they're going up by even more, 9 or 10 degrees. This is huge, and particularly if you're living in, say, Africa, where the temperature is already 35 degrees, if it's going to go up by another 7, then it's well over blood temperature. You can't work outdoors under those sorts of conditions. The precipitation is much more difficult to predict because of its very nature. The hash lines on those plots mean that we don't really know in those areas. So with regard to the lowest scenario, by the end of the century, you've only got the very vaguest idea of what the precipitation is going to do. But by the end of the century, it looks pretty clear that, for example, in the Mediterranean, it's going to be a lot drier, and also in the southernmost part of Africa, it's going to be a lot drier. And clearly that's going to affect the way people live in those regions. That's sea level. I'm going to skip on that because I want to talk about risks. You can think about risks in a number of different ways. This is sort of IPCC speak, but there's a different ways you can think about aggregated risk. So each of these bars is looking at a different particular risk, and it's showing what the magnitude of the risk is by the colour according to the temperature rise going up the bar. So the one on the left is things with limited adaptation capacity. So that could be coral reefs, for example, or might be other sort of species that just suddenly disappear. And you can see that the risks to those are getting very severe even by the time you get to 2 degrees relative to mid-century. The next one is the response to severe weather events. So I've already talked about temperature varying over the globe and it being different in different regions, but another important aspect is the way that the weather responds. And it seems to be quite clear that as you get climate change, you get more extreme weather events. So you get more heavy precipitation events. Even in the circumstance that the overall rainfall doesn't change, it comes in more intense periods. And then, of course, you get ground flooding and other responses. You'd also, very obviously, get more heat waves and those sort of things. That's the second one. I better whip through this, I know I'm spending too long. But the third one here is to do with the distribution of impact. So this is saying, actually, it's a reflection of the fact that some parts of the world are more susceptible and vulnerable. And it sort of happens that it's the poorest parts of the world, of course, who are the most vulnerable. Just that's the way it works out to climate change, and I'm sure that's the sort of thing you're going to be talking about today. The next one is rather the opposite. It's not looking at distribution, it's more looking like an aggregated economic effects. If you add up the economic effects over the globe, those are the risks for that. And finally, this associated with large-scale single events. So, if you've got a huge tropical storm or something like that. So the point to be made is all those things, the higher the temperature goes, the greater the risk you are of being subject to those things, but they vary between those different risks. And this is an assessment by a project, an Avoid project, which is, of course, these things are very difficult to predict. And you have to predict not only what the climate's going to do, distributed over the planet, then you've got to predict the impact on people. So this is very, very inexact science. But these are the indications. So by the end of by 2100, you can see 2 billion people with less water, 90 million being flooded, plant species being lost. It says 12 billion person exposures to heat waves, so that's obviously more than the population of the planet. This means that lots of us are experiencing, but also many people are experiencing it more than once a year. And then there's cropland as well. So I think I better, shall I carry on or shall I stop?
No, you've got another 3 minutes.
So I've got some very strange maps here. They're strange because they're showing impacts by national boundaries, which of course is silly because these effects are not going to be constrained by national boundaries, but they're looking at populations. And you can see by the colours the sort of which countries are going to be affected the worst. So this one, for example, is showing the likelihood that by 2100 the people affected by river flooding is going to be more than 25%. And the greatest risks there you can see are in Southern Asia and India and Bangladesh and those countries where the chances of river flooding are just almost definitely going to go up by more than 25%. That's for the low scenario. That's the 2-degree scenario. If you look at the 5-degree scenario, of course, the effects are much more over the world. So I'll just do another examples. This is heat waves already. Even with the low scenario, we've got large continental masses are being affected by heat waves. By the time you get to 5 degrees, everybody, all over the world, it's more than 25% of people are going to be suffering from heat waves with all the associated impacts on health, etc. Water stress is there's odd sort of geographical distributions on that to do with the sorts of crops that you grow and how you use your water. And finally, the suitability of cropland. There's some places, so for example in Canada, it may be that it's better for crops. But you can see for a large portion of the world it's definitely not the case. And that's more on crops. You hear nowadays some people talking about, as the CO2 goes up, the crops like it. They like it for their photosynthesis. And that's absolutely true. And you do get increased greening as the temperature goes up a bit. But there's other limiting factors. So the plot on the left there is showing how the 3 food crops respond to increasing temperatures. And by the time you get up to 40 degrees, those 3 crops basically, you can see lethal limits, they're dead, you can't grow them. So that's that. And then one on the right is showing particularly the effects on cereal crops in Africa, where the greening areas are suggested that it's actually more productive and the red areas are less productive. So again, it's very inexact and not the same everywhere. So I did a sort of little list of risks for Africa. I'll just leave it there for you to read. It's all the obvious things on water and food. There's also the effects on health issues, particularly disease, both transmitted by insects and by things in the water. You get non-communicable diseases as well, so as the temperatures go up, you get people suffering more from heart disease and all these sorts of things. And then you've got the whole thing about migrations of people and climate change as a multiplier of any sort of existing security threats. So even if climate change wasn't causing the effects in the first place, the fact that climate change is there is making it much worse, say, for people in Syria to try and cope with what's going on there. And I'll stop there.